Hello everyone, I'm Jae-myung Lim from Georgia Tech. I'm here to introduce our work, front-end circuit simulation for CMUT system based on an accurate nonlinear CMUT array model. Because CMUT behavior changes non-linearly with a DC bias, and also it has some complex acoustic interactions, so we need to do the FEM simulation for the CMUTs. But it takes too much time and it requires too much memory. It's nearly impossible to use FEM simulation. So we developed a MATLAB-based CMUT simulator, which developed by Dr. Satya et al. But the problem of this MATLAB simulation is you can't directly use the result of the MATLAB simulator to the circuit simulator. So we developed an equivalent circuit from the MATLAB simulator results to use the result to the circuit simulator. Here's our application. So we are developing an IVUS system which can be integrated on the Guidewire, not a character. Here, Guidewire. So we have strict size limitation. We have to integrate the system on 400 micrometer by 1 millimeter. So to make up the loss of the resolution from the size limitation, we increase the frequency to about 40 meters. It means we need a high frequency, high bandwidth front-end circuitry, which doesn't allow that much design margin. In addition to that, we can't put that much adjustability because, for example, if you want to change the bias of the amplifier, you need an extra interconnection and an extra pad, which is directly related to the increasing of the size. So, so in the designing phase, we have to accurately simulate the front end and the CMUT in the designing phase. Here is our CMUT in this study. So this is the top view, and this is cross-sectional view. The CMUT have 12 elements. Our overall size is 300 micron by 1 millimeter. The CMUT, one element have 40 membranes, size of 20 micron by 20 micron with a 25 micron pitch. The center frequency of the CMUT is 37 meters with a 12 megahertz bandwidth. We learned that simulation on the MATLAB simulator we developed for the one elements, including the acoustic crosstalk from the neighbor elements. Here we show that the impedance calculation results with a different bias. As you can see here, the rear part of the impedance goes up with a DC bias increasing, and the center frequencies goes down with the DC bias increasing. And also you can see the second peak here is related to the acoustic crosstalk. On the MATLAB simulator, we simulate the current output from the Gaussian voltage input of the CMUT. Then we divide the voltage input by current output to calculate the impedance of the CMUT. And also we calculate the velocity of the membrane to get the transform ratio from these equations. So we got the C0 and the transform ratio and input impedance of the CMUT from the MATLAB-based simulator, but it is that's the only thing we can get from the simulator. So we just want to make some simpler circuit model which can represent the CMUT accurately. So we use this. This is our proposed equivalent circuit. It consists of the C0 and the other all the impedance except for the C0 is represented to the Gmac, and pressure is represented as a voltage source here. Here we show the how we model the CMUT on the equivalent circuit. So we model the resonance of CMUT as a series RLC here, and the the peak from the acoustic crosstalk modeled as a parallel RLC. Because in the rear part of GMAC is here, So in the lower frequency, Gmac is following the RS in here. So we average the low frequency near part of impedance Gmac to calculate the RS, and the RP is difference of the peak from the RS. So we know the RS and RP from here, and also the peak frequency here is related to this equation. So we convert this equation for LS as a function of C0, CS, and F peak. So we we ignore the LP and CP because it's not that much effect on the rear part of impedance at the F peak. So we ignore the other parts, and we rewrote this equation for the Gmac to the CS equation. So this is equation. So because we know RP, RS, C0, F peak, so we can calculate the CS from this equation. And based on this equation, we also can calculate the LS. For the calculation of the parallel RSC part, so we just subtract RS, CS, RS from the CMUT impedance, and then this is equation. So because GP is following the second order equation, based on the second order equation characteristic, we can calculate the CP value from this equation, and also because the FC tog is caused by LP and CP resonance, so we can calculate the LP from the CP values. Here we show the tendency of the element difference based on the bias change. So to get a physical meaning of each elements, we converted electrical domain impedance to the mechanical domain impedance by using the transform ratio. And apparently CS, which is represented spring softening effect, goes up with a bias change, bias increasing. But the LS, which represents the mass of the membrane, and RS, the radiation loss, is more or less constant. And C0 is increasing by expected, and we are investigating on these parallel parts, meaning of the parallel parts now. So here we compare, to verify the equivalent circuit model, we compare the result of the equivalent circuit with the MATLAB simulator we have. So here we show the impedance, and here we show the current output when the front-end side is ideal. It means front-end side is shorted. And the results is agree well. To verify the model with a measurement, so we make a test setup like this. We connect the TIA CMUT with a TIA by using the wire bonding, like this, and we use our custom designed ASIC for testing it. Here's a block diagram of the test setup. So we modeled the wire bonding interconnection as a 2 capacitor and a 1 inductor, and we used a very simple TIA and a buffer to see the output of the CMUTs. We used six channel of the CMUT, and we show the results in next slide. Here, at the first step of the measurement, we measure the input pressure of the piezoelectric transducer. So we apply the input signal like this spectrum at the piezoelectric transducer, and record the pressure input by using the hydrophone. Here is a hydrophone measurement input pressure. Yeah. So we use the pressure input as the input of the equivalent circuit, and we run the simulation on the cadence. This black solid line represents the simulation results, and the gray lines are measurement of 6 elements. And here we average the six element measurement and compared with a different bias voltage, which agrees simulation. The measurement agrees simulation well in 3 dB difference, the CDTB is the uncertainty of this either one. So we modeled the CMUT as an equivalent circuit, and we verified the equivalent circuit with a MATLAB-based simulation and a measurement. And also, our future step is optimizing the front end based on the this equivalent circuit and develop a large signal model, large signal equivalent circuit. And I appreciate for support NIH and NIVID and UFFC Society. Thanks.